Welcome to this lecture where we will discuss AI errors and why it is essential to measure them to make compliance possible. Let's start with a bit of history from before AI ever existed. In the 19th century, there was a gruesome scandal with unsanitary milk from sick cows fed with industrial waste from the nearby distillery. The milk was so filthy it was doctored with plaster, chalk, and much more. It was peddled as pure country milk to the most vulnerable, including babies. And infant mortality is actually what urged the doctors to point at the milk. Although it was disgusting and actually deadly, it took decades to be fully addressed by regulations. Before the first regulations, it took a decade since the moment experts knew, and half a decade since the larger public knew. And before regulations fully addressed this food safety problem, it took 5 decades. There are lots of similarities between food safety and responsible AI. Problems arose from the large-scale industrialization of more traditional practices. It introduces new and untested technologies, but also new materials like food additive or data features. Their effects at large scale were sometimes known, and new effects emerge, having broad impacts on our health, economy, and society. Testing the products and informing consumers was not required. All sorts of claims could be made, and like selling snake oils that cures all things, AI is often marketed with exaggerated claims. Or the claims may just be to provide regular milk or regular data analysis, without mentioning its actual content. Overall, it was difficult to balance the interest of the public with the commercial interest of large corporations, even on issues as simple as mentioning the actual content of the products. Actually, mentioning the actual content was the first battle won for food safety. It preceded legal compliance. Roughly anything could be sold as long as it was mentioned with transparency on the packaging. It's a form of contractual compliance for the manufacturer. Yet, it is not ideal because it accommodates and perpetuates existing practices, and it puts the responsibility for the harms on the consumer. On a long road towards regulating AI, we have not even walked the first steps toward contractual compliance. We have no packaging to label and measure AI quality, no standards against fraud on AI quality, and no trade agreement for selling data and models. At the same time, it is harder to claim a prejudice because the impact of AI are largely undocumented. Food impacts the human body, and medicine can assess that. But AI impacts more intangible things like our social value or our mental health. So what can we do to achieve the same level of safety and responsible trade with AI as we did with food? We can at least measure the errors in AI results, same as we measure the nutritional or undesired contents in food. If AI errors are unknown, compliance remains hollow as regulations remain vague and imprecise. Now we will dive deeper into assessing AI errors. First with some basic concepts, before introducing basic methods to apply in practice. Classification deals with elements that can be in the right category or not. Classification errors can be seen like the quality of a bag of grain. The machine sorting the grains may let other things into the bag, like stones or straw. Regression is another form of AI. It predicts a number, like the price of a house. It can be like estimating the content of foods, how much cholesterol or pesticides in a cake. Regression deals with quantities, and regression errors occur when these quantities are over or underestimated. When we measure AI error, we only take a sample, same as we measure food quality with just a piece of cake instead of the whole cake. After taking measures from a sample, we assume that the errors are the same for all other cases. To recap, we take a test set to try the AI and check the errors it makes. because for this test set, we know what the true results are. For instance, we have manually classified the test samples. After that, we need to estimate errors for many other data sets. We call them target sets. Now, it is important to recap the names of the data sets that we are talking about. The test set is a sample used to try the AI. Ideally, it should be a random sample of the typical data the AI is meant to process. The training set is used to build the AI model, to let the AI learn from examples. It's usually a random sample, but we often use non-random samples, for instance by removing outliers. Finally, the target set is any data set on which the AI is applied. Ideally, it is also a random sample, but in practice, this is often not the case. For example, with computer vision, image quality can drastically change. And for classification problems, the class proportions can change too. For example, there are more or less cars or pedestrians to detect in a street. Because all these data sets are just samples, they can vary between each other. The error rates can change depending on which sample is used, which test set, which training set, or which target set. In practice, the training set remains the same. We assess errors for a given model that has already been trained. Some AI are tested with different training sets, for instance, to study the bias-variance trade-off, but this is not representative of the end usage conditions. In practice, there is only one test set, but as a sample, it can vary from the true error rate and from the target sets we will assess eventually. So the test set introduces variance. In practice, there can be many target sets, and they also introduce variance. So now we will focus on random variance. It is the small variations one can observe between samples that are randomly drawn from the same population, which is the whole set of elements to classify. Let's consider the simple case where test set and target set are both random samples. We can estimate the error rates in each sample, and the difference between rates from random sample have been well researched. The range of values have well-known variance and a simple formula. It's a simple fraction with the sample size as the denominator. So the smaller the sample, the higher the variance in error estimates. In practice, we use the error rates in one sample to estimate error rates in other samples. We use a test set to estimate the errors in a target set. In this case, the error estimates have added variance. One component of variance is for the test set with the test set size as a denominator, and another component is added for the target set with the target set size as a denominator. So both sizes matter. The smaller the test set, the higher the variance in error estimates. In other words, error estimates are more imprecise. And for smaller target sets, their error estimates are also more imprecise. Other data features may vary across samples. Typically, the class proportions may vary. For example, there can be more or less cars and pedestrians to detect in a street. Variations can be random and small, and we can calculate the combined variance for class proportions and error rates. The variations can be more significant and non-random. For instance, in the visual, we added more of the gray object. The AI would detect more gray objects, and the AI would also make more errors and misclassify more gray objects as orange. We can still estimate the errors in a target set, but we need specific math. And using these calculations will increase the impact of random variance. There is basically more uncertainty. We have reviewed the basic concepts for estimating AI errors, and we outlined issues with random and non-random variance. To conclude this lecture, we will now discuss how to apply error estimates in practice. We will see why variance is so important to support fair, transparent, and accountable AI. error estimates can vary between samples. So measuring a single error rate provides limited information. What could be the error rate in another sample? Fortunately, given the variance of error estimates, we can calculate the range of values to expect in other samples. This is called a confidence interval. It can estimate the range of values that most samples could take, for instance, the 99% of the samples. Confidence interval can also be smaller to exclude the most extreme value. For instance, the interval for 90% of the sample would exclude 5% of samples with the highest values and 5% with the lowest values. We can compute intervals for any confidence interval. For instance, half of the sample would fall within that range around the mean, showing the most common values. These confidence intervals are crucial to support AI compliance. If we seek to limit the errors we can tolerate, without variance we cannot estimate how many of the target set will not comply with the limit. In this example, we can see that 25% of the target set will not comply with the limit. For example, if an AI is applied to detect bus passengers, 25% of the target samples, which is 25% of the buses, will have errors above the limit. Finally, variance is also essential to assess bias. For instance, an AI can discriminate women by yielding more errors than for men. We might see that women's error rate is higher on average, but we can also see that 50% of women have higher error rates than ever expected for men, except for the most extreme cases. This concludes this lecture. If you want to read more, we attach some research papers underneath this video lesson.